Welcome back to the deep dive. Today we're looking at something really fundamental, maybe even a bit jarring. We're exploring where our standard electronics toolkit um, kind of breaks down. Yeah, we're talking about that comfortable world of R, L, and C components on the circuit diagram. We're going to see where it just dissolves.
Hmm.
Our mission, yours and ours, is to get a handle on the physics when AC frequencies go way, way up, so high that the actual shape and size of things matter more than the component label. We're moving from those lumped elements, RAL, LC, to thinking about fields, electric fields, magnetic fields, Maxwell's equations running the show. We're going deep inside the components themselves.
That's exactly right. It's a really critical transition point in understanding electromagnetism. See, your basic circuit analysis, where you just assign an impedance Z to everything, it works great at low frequencies. But push that frequency higher radio, microwaves, and the model fails completely. This is what you might call the high-frequency barrier. To understand modern tech, like communications gear, radar, you have to stop thinking circuits, start thinking fields.
Okay, so let's hit that reality check. Where do the textbooks often simplify things too much? We usually write impedance as Z equals R plus I omega L plus 1 over I omega C. But real components aren't ideal, are they? Take a resistor, just a piece of stuff physically. But that length has some inductance, L, and its ends being separated have some capacitance, C. We call these parasitics. They're always there messing with the ideal picture.
Yeah, they are. And the inductor is maybe the poster child for this breakdown. What is it? A coil of wire, many turns, right? It definitely has resistance along the wire. That's expected. But the killer is the capacitance between the turns. Every loop is near the next loop. At low frequencies, okay, the current flows around the coil. That's the inductor path of least impedance. Makes sense. But cranked up omega, the frequency, the inductive impedance, omega L, it shoots up. Meanwhile, the capacitive impedance, 1 over omega C, it plummets. Eventually, you hit a frequency where it's actually easier for the current to jump across the turns through that parasitic capacitance than to go all the way around the coil.
Wait, jump the gap.
Okay.
So it just stops being an inductor.
Pretty much. It behaves like some weird resonant circuit you didn't intend to build. Push the frequency even higher, and who knows? Maybe it acts like a short. Maybe it radiates energy away like an antenna. The point is, the thing you bought for inductance isn't just an inductor anymore. It's this complex, distributed thing. You can't fix this by just adding more R's, L's, and C's to your drawing. You have to look at the continuous fields inside.
Okay, that makes sense. We need to zoom in. So let's take the simplest case. The parallel plate capacitor. We always assume the electric field, E, inside is perfectly uniform, just straight across. Let's see how high frequencies wreck that idea.
Right. So imagine you're driving it with a really high AC frequency. Charges are sloshing back and forth on the plates super fast. This means the E field between the plates is changing rapidly in time. It's going up, down, up, down. Now, Maxwell's equations tell us something crucial. Ampere's law, with Maxwell's addition, says a changing E field creates a magnetic field. So this sloshing E field generates a circulating magnetic field, B looping around inside between the plates.
Okay. And there's the feedback loop, right? Because if the E field is changing, the B field it creates must also be changing in time.
Exactly. And what does a changing B field do?
Faraday's law. It induces an electric field.
Precisely. Faraday's law kicks in. This changing magnetic flux induces another electric field. Let's call it E2. This is a correction field. It's induced by the B field, which was induced by the original E field. And this E2 is what breaks the nice uniform picture we started with.
And how does it break it? Is it uniform?
No, that's the key. Because of the geometry, the B field loops around the center, the induced E field, E2, it isn't uniform. It actually varies with how far you are from the center of the plates, the radial distance, R. So the total E field is no longer this flat sheet. It's warped.
Wow. Okay, so E and B are constantly creating each other, influencing each other. That sounds complicated to describe mathematically.
It is. The full solution, figuring out exactly how the E field varies across the plate, it involves solving a wave equation in that circular geometry. And the answer comes out in terms of a special function, a complex infinite series, actually. It's called the Bessel function, J0 of x.
The Bessel function, J0x. Okay. Sounds complex, but what's the key takeaway? What does it mean for the field?
The takeaway is that the math confirms the physical picture. The field isn't flat. The Bessel function describes this pattern. The E field ends up being sort of weakest in the middle and stronger out near the edges, which completely changes the capacitance and the impedance from what you'd expect.
Okay, so the math describes this complex field pattern. What else does it tell us?
Well, this is where it gets really profound. That Bessel function, G0x, it's an oscillating function, like sine or cosine. It crosses zero at certain points. The first time J0x hits zero is when its argument x is about 2.405.
A specific number, 2.405. What does that mean physically when the function is zero?
It means that under those specific conditions, the electric field right at the very center of the capacitor plate goes to zero. The whole system enters a natural resonance. And remember that variable x, it depends on the frequency, omega, the radius of the plates, and the speed of light, c. So for a given frequency, if you make the capacitor plates just the right size, the right radius r, boom, resonate.
So the capacitor itself, just because of its size and the speed of light, becomes a resonator, not just a capacitor anymore.
Exactly. It stopped being a simple component. It's now a self-contained electromagnetic wave system, oscillating all on its own at that frequency. Its geometry dictates its behavior.
That idea that geometry dictates resonance seems really powerful. Where does it lead next?
It leads to the ultimate version of this, the resonant cavity. Imagine taking our parallel plate capacitor, but now, instead of open sides, you enclose the whole thing. Wrap metal walls all around it. Make a sealed metal can, say, a cylinder.
Okay, a closed metal cylinder, like a tin can.
Right. Inside this perfectly conducting can, the E and B fields can now form stable standing wave patterns. In the simplest, lowest frequency mode, the fundamental mode, the electric field lines run vertically, up and down, parallel to the axis, just like an arc capacitor. And their strength still varies with radius according to that Bessel function, J0, weakest in the center. Meanwhile, the magnetic field lines, B, they circulate in horizontal circles around the axis, perpendicular to E.
So it's like a wave trapped inside the can, bouncing back and forth.
Exactly like that. E and B are perfectly out of phase by 90 degrees in time. Energy sloshes back and forth between the electric field and the magnetic field. And here's the crucial advantage. The quality factor, the Q.
Ah, Q factor. How well it stores energy versus losing it.
Right. Because the fields are totally enclosed, and the walls are really good conductors, there's very little place for energy to leak out or be dissipated. The only loss is due to the tiny currents flowing just on the inner surface of the walls, within the skin depth. This means these cavities can have incredibly high Q factors, like way over 100,000 if you use silver or copper.
Wow, 100,000. Compared to maybe a few hundred for a good LC circuit?
Easily, which makes them fantastic frequency filters or oscillators. Much, much better than any lumped RLC circuit you could build. This is the kind of tech that made high-power radar and modern microwave communications possible.
And like a guitar string having harmonics, I assume the can doesn't just resonate at one frequency.
Good point. No, it can support higher modes, too. More complex patterns of E and B fields inside, each with its own higher resonant frequency, all determined by the can's dimensions.
So how do we tie this all back? How do we connect that simple LC circuit idea to this sophisticated resonant cavity? Is there an intuitive link?
There is. You can sort of think of the cavity as an LC circuit where the L and the C aren't separate components anymore, but are distributed in space. Their functions are separated geometrically.
Okay, help me visualize that. Start with a normal LC circuit.
Right. Now, imagine you take the capacitor plates and start pulling them apart. You're increasing the volume where the E field exists. At the same time, you're changing the loop path for the current, which affects the B field and the inductance. Now, keep pulling them apart, but start adding conductive walls around the whole thing, gradually enclosing the space.
Ah, okay, I see. You're morphing the LC circuit into the can shape.
Exactly. In the final cavity, the capacitance function, where the energy is stored in the E field, is strongest near the top and bottom plates, or the ends of the cylinder. And the inductance function, where energy is stored in the circulating B field, is dominant in the central volume, sort of in the space between where the E field is concentrated. The whole physical shape, the geometry of the can, is what links these distributed L and C effects and sets that single resonant frequency.
That's a really neat way to picture it. From lumped elements morphing into distributed fields defined by geometry. So looking back, we started with simple circuit components failing at high frequency as parasitics took over. Then we saw how even a basic capacitor becomes complex, with internal E and B fields generating each other, described by Bessel functions leading to resonance. And finally, enclosing that system gives us the resonant cavity, an incredibly efficient high-Q device where geometry is absolutely everything. The big takeaway for you listening has to be this. When frequencies get high enough, you leave classical circuit theory behind. It's wave physics, Maxwell's equations, and geometry that rule.
Absolutely. And maybe a final thought to leave you with. It's the hidden complexity in simple things. That parallel plate capacitor, day one stuff in circuits class. Pushed to high frequencies, it reveals the whole deep, beautiful physics of electromagnetism. It transforms from just a component into this sophisticated wave system governed by geometry and described by some pretty advanced math like Bessel functions. It's quite amazing, really.
It really is. A fantastic journey into the physics behind the components. Thanks for exploring this deep dive with us. We'll catch you next time.